All right, good morning. How you guys doing? All right, so today we're going to talk about sedimentation, but really move past that onto coagulation and flocculation so that we can improve our sedimentation. I wanted to follow up real briefly with a couple of notes here, something I wasn't very clear on, and I'm meant to be clearer last time when deriving our equation here for V naught, that our critical settling velocity, or the design settling velocity, should be, we should be able to know it essentially based on our hydraulic retention time. And one of the things I didn't quite point out was, if we look at the height, the distance that we have to travel for some particle, we call that height, and we have some time in which it needs to travel that, the time that the water stays in our sedimentation chamber, that's theta. So it's the velocity then is the distance per time is the height divided by theta. And so when we take that approach and we consider what theta is V over Q, we can say that that's going to be equal to H divided by the V, which in this case would be the area of the basin times the height divided by Q. We can translate that, or we can see that here the H's will cancel, and we're left with 1 over AB over AQ, which becomes Q over AB. So that was one step that I was not nearly as clear as I wanted to be for you, but that's the derivation to think about. Okay, this particle has some distance to travel, some amount of time for it to travel there, and we can get our reactor dimensions accordingly. So that's the definition of that critical settling velocity. That's the design key for a given reactor. Okay, then we went on to this problem, and I later realized I think I had a calculation error somewhere in my Excel sheet, because I think this was supposed to be 10 to the minus fifth, and then that would be Vs was not, was less than V naught, and so then that means that not all particles were removed. Feel free to double check that as you go through the calculations. I think I just did something in Excel, one digit wrong, solved it later, and it was coming out 10 to the minus fifth. But you can see in either case, if it's Vs is greater than, we see all particles are removed, and we understand that. If it's less than, then not all particles are removed. So I'll these corrections will be posted when I after class today, so you can review that at your leisure. Was anybody questioning this last time? Like, wait, I had it almost, but not quite. Just didn't quite get it. Okay. All right. So then we started talking about kind of the particle sizes. So we've covered sedimentation essentially now. Next up will be coagulation, and I'm going to tell you a little bit about surface chemistry of particles and how we can manipulate that to cause them to stick together. And from there, we're going to get into flocculation, which is essentially, once we cause the particles to stick together, they're going to do so in a sort of a first order reaction in a chamber that we give them, typically a CSTR. And so we can consider, okay, well, what dimensions of a chamber do we need to give them the proper capacity to clump together, and then how big are those particles going to be at the end of whatever time we give them. So that's what we're going to work on today. We talked about how there are some particles that are exceptionally small. We don't really think that there's any way to get them to settle in any meaningful manner under normal circumstances. You could, for example, settle viruses out of a tube by centrifuging at a very high speed to get a artificially very high gravity, so to speak. But that's quite a bit. It's much easier to do that with bacterial cells. You have to actually have a very strong centrifuge to get viruses to do that. Okay, so when we consider particles floating around in water, we'll want to remove them. We're going to talk about a concept called particle stability. And when I say stability, what I'm referring to is if they're stable, that means they're not sticking when they touch something. You know, they don't get stuck. They're stable in the sense that they're not going to stick together and then fall out of solution. So they're sort of socially distanced, free, happy, like repelling other stuff around them. And that's what we call stability. So when we say we've destabilized the particles, that means suddenly they're acting a little more like Velcro when they meet another particle, starting to stick together, and ultimately they will fall out of solution by sedimentation typically, or just sticking to some surface. And that's what we call destabilized. So stability, they will continue to be suspended in solution. So for the sake of easier sedimentation, we want to destabilize them. There are two primary forces that we consider that could cause them to be stable or unstable in solution. First would be electrostatic repulsion. So this would be any particle with some sort of a charge. If they have like charges, then those charges will repel each other. So typically, there are some good reasons for this. Typically, most particles floating around in water tend to be negatively charged. This has to do with acid-base chemistry quite often, with the fact that there are potential for OH groups or carboxylic groups, all sorts of different functional groups that can give away a proton, an H+, and then the remaining charge that's sitting there will be a minus. That will be pH dependent, so if you put it in really acidic conditions, you know, that could change things. There are also scenarios for inorganic materials, like clay particles or something, that they may have atomic substitutions, giving them a net negative charge at the surface. At any rate, it's very common for stable particles to be negatively charged. That's the typical situation, and surfaces in general. So this electrostatic repulsion then is a long-range repelling force for most particles, because most particles are negatively charged. So the typical interaction there would be this electrostatic repulsion. I'll label this as 1 there. Another force, or really a set of forces, is what we call the van der Waals forces. These are a mixture of kind of a variety of atomic level interactions that can cause molecules, atoms, particles to attract to one another. But the deal is this happens at a very short range. These include things like the electron clouds around the atoms, around the molecules. Once they start interacting, sometimes that can act as almost like a magnetic field. You can also have actually direct magnetic fields, or other attractive, very short range things that are typically, if you get close enough, these will be, we'll draw it this way. These will be attractive, but there's that limited range. So this would be the second version here, the second thing. The reason the ranges are so important here is the electrostatic repulsion tends to fall off as a distance of, I believe it's 1 over radius squared, whereas the van der Waals typically are 1 over radius to the 4th, or even in some cases 1 over radius to the 6th. So if you remember looking at gravitational fields, things like that, magnetic fields, you'll recall, or playing with a magnet, maybe that's the easier one to remember, you'll realize that when they get really close, wow, that becomes really strong, either if you're trying to push opposite poles to each other or pull magnets apart. It's not hard either way if they're this far apart. But once you get really close, you can really see that force has magnified. It's the same thing happening here, just on a kind of a nanometer scale. So the electrostatic repulsion then, you can typically feel maybe even out up to 50 nanometers, probably less than that. Whereas these van der Waals forces are typically less than 5 to 10 nanometers. I'll say 10 nanometers. Both of these I think are probably a little less than these. Okay, so then there's a big question about how do we shrink this electrostatic repulsion effect. And this brings up a concept called the electrical double layer. I've got a slide or two to explain that. But while we're still here with my little sketch, what I'll show you is that if you have this negative charge, the natural thing for the solution to do is to allow or to have any positively charged ions in solution will make it kind of a layer around that negative layer, right? So if you have sodium ions or iron 2+ or 3+, they will tend to accumulate in a layer. Now these are free floating dissolved ions, but they will migrate next to that border. There's going to be some diffusion involved. There's going to be some motion. It's not like they're stuck there, but they're going to be attracted to that vicinity. And then likewise, you'll get a second layer. So this is where we call it an electrical double layer, where even more randomness here, but you will get a second layer of negative charges kind of at that front. And what you see here, and it's not perfect, there's going to be some positives around somewhere, but what you see, especially if I just simplify it a little and ignore those right there, is two layers of negative charges coming close to in contact. So instead of this electrical field, perhaps the electrical field is 20 nanometers in effect from the surface, but the fact that there is an extension by this double layer of ions out into solution, it pushes it a little further. So this is what's keeping them at an arm's distance from one another. So that's one thing, that's the primary driver for our electrostatic repulsion, and how it reaches out into solution has to do with the ions in solution. So we could say these ions in solution are a key to the distance. Okay, so that means if we can control those in some manner, maybe we can control the distance to which these are repelling each other. And that's the core principle of a lot of our coagulation. So here's another scheme of it. You can see that we have a bunch of ions. We have some solid surface that probably has a negative charge on average at the surface, so it's going to attract that first layer of positive ions. And then this second layer, double layer there with the negative. So one thing you can notice is in this condition, if you had, rather than just sodium plus, if you started adding, let's say, calcium 2+, now every time you have the same size of one of these, if it had 2+, then you wouldn't need this one here. That one charge would satisfy that one ion, smaller space, to satisfy more charge. So that 1 2+ could give us kind of a shrinking of the space required to fill that charge, to satisfy that charge right there. So if you replaced all of these 1 pluses. With 2 pluses, you'll see this distance shrink because they're physically occupying less space. And then you can also consider if we did Al3+, so aluminum, would do that to an even greater extent. So these will compress the space with which we're satisfying the charges. Okay, so if we take a look at what happens practically when we do exactly that, and we say, well, maybe we had sodium. Let's take a look at this larger figure on the right first, 3-6. So this is showing us, it says a schematic coagulation curve illustrating this DLVO, that's the van der Waals forces, basically, this interaction of when do they become sticky. Theoretical relationship between charge and dose to achieve a given turbidity reduction. So turbidity, you'll remember, I hope, that is essentially the cloudiness of water. If you have particles scattering light, it's not absorbing light like a tea would do, but if you think about the small particles that would be in coffee and make it so that you can see through tea, it just colors it brown. Coffee, you don't typically see through because there's actually small particles suspended there. Or if I shake my water bottle up a whole bunch, the bubbles for a moment are causing turbidity because they're scattering the light. So while you have a whole bunch of bubbles in there, if you ever got water from a water fountain, filled a bottle, and it looked like it was milk or milky, and then you let it sit a few minutes, and that turns out that it was just really fine bubbles. I don't know if you've ever seen that, but occasionally the water fountains will do that, and it's just really fine bubbles scattering the light and makes it look like milk, which is also turbid. So turbidity is this concept that is a measurement of how many particles are in there, okay? So when we say a reduction in turbidity here, or residual turbidity in percentage, if we start at 100% and go to some level, in each of these cases, we're starting at 100 and they just cut off the rest of that there. What they're saying is we have all the particles are still there, they're still hanging out in there, and then at some level of this added salt, we have a drop off in turbidity because we've destabilized the particles. Suddenly they're starting to stick together and our remaining turbidity drops like a rock. So for the sake of causing that to compress that double layer, like I was talking about a moment ago, to squeeze that down to the point, it's not technically correct that they'll just stick right next to each other. There's going to be a little bit of separation, and in fact, if the solution itself is very dilute, is very close to pure water, that separation is going to be bigger because there's an osmotic pull to try to spread the charge out over the entire solution. So there's a role of osmosis here that I didn't mention, that wants there to be a gradient. So if the bulk liquid has a whole bunch of ions, it's going to push this double layer shorter because there's no pressure to pull them out. If the bulk liquid is very, very pure, very, very dilute, then it's going to extend this double layer outwards. So then that's why adding this salt, we expect to compress it, even if it's just sodium salt. It just takes a lot of sodium salt. So if we're just using Na, it's taking 10,000 milligrams per liter or 10 grams per liter before this hypothetical solution has that needed destabilization to cause the particles to stick together. If we use calcium with a 2+, then it takes only 100 milligrams per liter for the same effect. And so what you see here is that density of charge is making a very, very big impact. In fact, if we go to aluminum, so a 3+ charge, it's only 10 milligrams per liter to have that same effect. So this charge adding the extra charges is having a very, very large impact. So from 1 plus to 2 plus, that was 100 times different, and then 2 plus to 3 plus was another 10 times different. So when we select some salt to add to our water, if we're going to add salt to our water, there's a few things to consider. First of all, we don't want to drink seawater, so we don't want to be drinking 10 grams per liter. That's like the salty part of Lake Pontchartrain. At some places it's 5 milligrams per liter or 5 grams per liter, but as it heads out to the ocean, it's probably getting up closer to 10. So we don't want to drink that, and salt is pretty hard to remove from water typically, at least sodium, like sodium chloride, for example. Calcium is a decent option, and there are ways to remove it easier than sodium, but still we probably don't want to be adding that and adding the cost at that level to remove it. So aluminum is actually what we typically use, so in the form of alum. So it'd be Al2 SO4 3. We'd call it alum or aluminum sulfate. And what we get there is 2 aluminums, so 2 Al3 plus, and 3 sulfates, which would be SO4 2 minus. So we're actually getting quite a lot of charge for every one of these molecules that we add. And that charge is great because then we're really compressing that electrical double layer quite effectively, and we're not adding much of it. It also turns out we can cause aluminum to come back out of solution to precipitate it very easily. Oftentimes we'll precipitate it in a manner that also is creating particles for stuff to stick to. So it's kind of a win-win to use aluminum here. All right, so the other little graphs here are showing x-axis as distance. If you see that, and that's in nanometers. And on the y-axis, it says potential in millivolts. This is really just measuring the charge, the strength of the charge as a function of distance away from some surface. And so we can measure the charge as we add different conditions. So in this first one, sodium chloride here, 60 milligrams per liter of sodium chloride, we can measure a pretty strong charge. Well, let's call, for example, 30 millivolts as a decently strong charge that should probably keep particles separate from each other. Okay, so if we look at something like that, we see a reasonably strong charge with 60 milligrams per liter of sodium chloride all the way out near 20 nanometers. Now, if we change and take a look then at the calcium, let's see. Oh no, excuse me. This is changing the amount. So if we add 600 milligrams per liter, then we notice it's happening somewhere around 5 to 6 nanometers out of solution. And then finally, if we do 6,000 milligrams per liter, then we're really getting to that point where we are maybe 3 or 4 nanometers into solution. We can measure a charge that might repel each other. So here's kind of what you can see. That last one is really getting pretty close to where we could start seeing some destabilization. So you really get a sense of, we have to shrink it to kind of less than 5 nanometers out into solution before these van der Waals forces take over and start causing them to stick together. Another way to look at that would be in this graph at the bottom. For some given amount, we are changing from a Z, so the charge of our particle, as +1, that would be like a sodium or potassium or something, to a +2, to a +3, and again we could look at, for some arbitrary amount, we could see that distance that we can observe this charge into solution changing. Okay, so this is just 3 different ways of looking at this compression of the double layer that will cause particles to stick together. This is also why, if you were to look, if you were to take a boat and go from some estuary system where you have a lot of sediment in the natural waters, from the rivers and everything. It's, collected all the sediment, it's suspended particles. As you go out into the open ocean, you will start seeing that that's sedimenting. That creates a delta. And then once you get away from when all that has actually occurred, you'll find that the water is much more clear in terms of turbidity. So you'll see open ocean water typically will be not very turbid because things are not able to stay stable. Particles are typically not able to stay stable with respect to one another, and they're going to go through this coagulation, flocculation process and then sediment. Okay, so how do we quantify this? Real quickly, you've seen ionic strength before, I'm sure, in chemistry. So just as a reminder, the ionic strength of a solution, we can define that as 1/2 of the sum of each concentration times its charge squared. So we'll need this occasionally here for for understanding, okay, what is the charge strength of a system. And this is always going to be in molar units. So we would say, in this example, I'll let you kind of do it on your own for the most part. But if we were to say magnesium chloride, that's going to dissociate into magnesium 2+ and 2 chlorides 2-. What we would do is we would find, if we've got 100 milligrams per liter, we would find some value of magnesium 2+, and we would find the value of chloride, Cl-, and then we could say the ionic strength is going to be equal to 1/2 times the magnesium concentration times its charge squared plus the chloride concentration, Cl-, times its charge, -1, squared. So you see this, the square will always remove the negative, and we would solve it that way, right? So I think that should just be review. Feel free to work that example. I'm going to, for the sake of time, continue on unless somebody would like me to pause here. Another example you could consider as well, that maybe you have 2 sources of chloride, so magnesium chloride and sodium chloride, and in this case you would get magnesium, you'd get sodium, and you'd get, from both of them, you're getting chloride, so the combined you'd have 1 value of chloride concentration. And in this case, your ionic strength, again, should be pretty simple here. You can solve it like this. And get your answer there. Okay, and it might be interesting to compare, okay, you've got 50 milligrams per liter of MgCl2 plus 50 milligrams per liter of NaCl. How does that compare with just 100 milligrams per liter of MgCl2? You could also look at how much of an impact when you have aluminum, so Al3+, for the same mass, you'll see that the ionic strength is having a big role there because we've got that exponent of the charge. Okay, so that brings us to flocculation. I think I probably have some other, I might or might not have another slide. One other thing I'll say about sedimentation, just to add a little bit of flavor here, is when we look at 2 particles, another coagulant we can use is actually a polymer. And a polymer is meaning a long branch of molecules that have been stuck together and linked together. So polymer is a fancy term to say that we've taken monomers, which maybe styrene looks something like this, And then to make polystyrene, then you bond them together. And so then now this one attaches to the next one in line, and it might look something like this, where you've attached those, and so on. So you've made a chain of monomers. They can be all sorts of stuff. DNA would be considered a polymer because you've got these base units. They've attached together and made a chain kind of thing. So polymers are kind of everywhere. There are plenty that are food safe, but we can use polymers sometimes to act as a branch, especially if we have some that have a positively charged head and then some other stuff, and then another positively charged end, maybe a tail. They could act as a bridge to grab these two particles by their charge and bring them together, right? And so if we add in some polymers that have charges like this or are generally sticky with respect to the particles, then they can also help destabilize a solution. So polymer coagulants are fairly often used. Similar principle, so just wanted to make that little note here. So there are a few other ways we can kind of manipulate the particles' stickiness in that manner. So you'll see that in practice. But for the sake of kind of how it works, why it works, that's the deal, right? Is we're overcoming this electrostatic repulsion, and that's the core of what I want you to take away here, and to hopefully learn a little bit about that electrical double layer, so you know a little bit about why and how surfaces are sticky to one another. Actually, another interesting little factoid is the reason a gecko can stick its sticky pads on the cleanest, most the flattest surface ever is actually because it's using those van der Waals forces. It's getting its little sticky pads close enough so there's like very little hindrance to the proximity, so that the van der Waals forces can take effect, and it's using essentially that force to stick, which is not something that most of our experience, our surfaces don't allow that, right? Okay, so flocculation then. When we want to create this, we want to create an environment for the particles to stick together. We do the actual encouragement of them to stick together in what we call the flocculation process. So this will be gentle mixing, enough to let particles meet each other, but hopefully not so turbulent that they will also be ripped back apart. Because you can imagine stirring very fast will cause some shear forces. Particles will be essentially, rather than given a chance to stick together, particles that maybe did stick together would be pulled apart, right, if you stir too fast. But if it's too still, you're just relying on diffusion, and especially with particles this size, they may never meet each other. So you want enough mixing. So a gentle mixing is what we want. Collisions without turbulence. The goal here is to reduce the concentration of particles. And pause a moment to think about that. Our goal is to increase the particle size. And to do that, we need to take particles, let's say 5 particles over here, or let's say, 1 particle here, 1 particle here, 1 particle here. If those 3 stick together, that makes one larger particle, and now we have fewer particles in solution. So we're going to reduce n. This is the number, well, I have it written there, the number concentration of particles. If we reduce that, inherently, we're not changing the size of these little individual particles, then we must be making larger particles. Okay, so that's the logic here. We don't actually care how many particles are there, really. What we want is for them to be larger, so that sedimentation can then remove them. All right, so then that might look like, if we have some bit of water, we have, let's say, 6 particles there, and now in a same volume of water, now we have one particle that is an aggregate of all 6 of those particles. So this just went from n equals to 6 to n equals to 1. And I'll call this our n initial, right? So we say n naught is 6 particles per milliliter or whatever volume I just drew. And then now we have 1. So that, thinking about it that way, you might start to realize that if we have some rate of change of these particles, we can actually relate that quite nicely to some reaction rate. And our reaction rate balances often had n over n naught, or we could say, we could even flip that. As you'll see, it will make some sense, and manipulate these mass balance terms into a form that will tell us something about how many particles we have versus how many we had moments ago. Okay, so then the question becomes, how do we know the rate at which they are aggregating? Because we want to know that rate in order to know how big a chamber we need, how long the particles need to sit here, how fast do we actually need to stir. So the rate at which they are aggregating is going to depend a lot on several factors. First and foremost going to be the mixing conditions. So we will describe the mixing conditions as with a term called G. So this will be our mixing intensity. We have a definition of it. You'll see this is in per time units. And the definition or the equation here is going to be the square root of the power that we add to the solution. So with our stir bar, with our mixer, divided by the viscosity of the solution, the water, divided by the volume of this flocculation basin. So I have each of these terms written out here. This is an equation that will be on your exam sheet, so get familiar with the terms here, what they mean. And we could describe or depict what's happening here if we take a look at what happens if water is moving along a surface. Now this could be the surface of a paddle wheel mixer, or the surface of the basin wall that the water is moving by. I guess you could also even consider this the surface of some particle. So we're going to look at how the fluid is going to move next to it, and if we have some velocity of the fluid going by our surface here, we can imagine that next to the surface we have some resistance, some drag force, given the viscosity of the water. So as we move a little further away, we will have a bit less drag force, up to a point where eventually we reach kind of the bulk solution, and then this would probably stay constant after some point. But near the surface, we could draw some sort of a gradient, and we could say that gradient might look like this. And what we're looking at is some change in the velocity term as a function of distance from, if this is y, distance out away from the surface, then what this little gradient thing is showing us is a change in velocity per change in distance, right? And if you look at the units of that, that would be distance per time divided by distance. So this goes to 1 over time. So that means this gradient here is g. And we'll leave that in per second. So essentially what I'm showing you is we can measure this mixing intensity based on how the velocity is changing as it's close to or farther away from the surface. So that's our concept of G. That's what it means kind of in a physical sense. And this is why it's relating to the power that's added. How strong are you stirring? How viscous is the stuff, right? It would be different to stir pure water compared to ethanol compared to syrup, right? Each of those have different viscosities. They're going to be acting differently as you mix them. And then this VB, the volume of the basin. So if you had a 1 horsepower little motor thing and you're trying to stir an Olympic swimming pool, you're not getting much mixing intensity, all things told. And now if you did that in my 1 liter bottle of water, that's probably going to be quite strongly mixed. You can intuit that very easily, and you can see why that volume term is important there. One thing to note here is we're going to keep our units in kilograms, meters, and seconds. So my 1 liter bottle, I'd have to convert that to meters. If we're going to keep power in watts, and each of those units. Okay, does that make sense? All right, so these collision reactions, as we're flocculating, we can describe this rate as dN dt, and we've already mentioned that K, this mixing intensity is going to go into the K, and we'll finish out the other things that go into the K in a moment, but I'm just going to pause us here and say this dN dt, we can describe that as negative K times N. So N again being the number of particles per volume. And this is going to be to the 1 power, because if particles stick to one another, then the reaction depends on how many particles are there. You're not going to have any reaction between particles if there's only 1 particle, right? So it does depend on how many are there. And so our reaction order is going to be a first order, and because they're sticking together, reducing the number there, it's going to be a decay reaction. So this becomes a first order decay, so we can write this as the reaction term is dN dt equals negative Kn. As N decreases, the size increases. So I've already drawn this up for you, but this was my spot to do so. And one thing that could happen is, if we have, I don't know, 8 or 9 particles there, we might end up with a system where we have, we have not caused all of these to come together, but just some portion of them, right? So in this case, let's say that, I didn't count exactly, but this looks about like that, right? And so this would tell us, okay, for each initial particle, we have 3 final particles. So that means there are 3 particles. We could say for each initial particle this N naught over N would be initial per final particle. Meaning that the volume of the final particle, in this case, if N naught over N equals 3, that means each particle is 3 times the volume of the original particles, right? So we can see that spatial relationship right now and work towards, and see how we can work towards a size difference. Yeah?
You said 3 means it's 3 times what?
So if our value for N naught over N is equal to 3, you see how that worked, right? That was, then that means that there are 3 initial particles in each of the final aggregates. So there are 3, and great question. This sentence here is actually quite important for all the flocculation stuff. To recognize the interaction between this analysis, this N naught over N, to reality is actually really helpful to understand for these problems. And you'll see word problems phrased in this manner, and that's part of why. So 3 initial particles in each, you might see it just written as aggregate. that could get a little confusing if maybe you did 2 different flocculation attempts and you had these very small initial particles, you made some aggregates, and then you gave those another chance, and then you made new aggregates. So initial versus final particles, or however you want to call it. We'll say final aggregate. Okay. So that's kind of the fundamental term. And now what you'll notice is when we do a mass balance, oftentimes we actually care about how many are remaining compared to how many we started with. In this sense, we're sort of inverting that to look at how big the particles became, right? How many of those initial ones are in each of the final ones. That's a little more useful. If you solved it for n over n naught, then you can just simply invert it afterwards. That's fine. But you'll notice here that the mass balance, we're using it in the same manner to achieve some numeric outcome, but we are rearranging it. Okay, so I've got another set of slides where we'll pick up right there. Let's go ahead and keep that. Okay. So we talked about that. All right. So about this rate constant, this K, we want to know what all goes into it. We've already talked about G, and we kind of have a good idea now of where and why we're using that rate constant so that we can kind of see where we're going with it. So there's G, but there's also this omega term and this little alpha. So this guy is the collision efficiency. So if we have completely destabilized our particles, that means every time 2 particles meet, they stick together. So this is just a kind of a ratio value that says, given 10 collisions, how often are they sticking together? If the answer is 10, every 10 collisions, you get 10 new aggregates, it's 100%, right? It's 1. If it only happens half the time, 5 out of the 10, then this alpha is 0.5. So this is just a fraction we can use to describe how well destabilized the particles are. It's not, and from the sense of a rate constant, you can see that if this were to be 0, they're completely stable, you don't have any flocculation, right? And if you have 100%, then all it's saying is, this is just a value of 1. Consider all the other parameters to know your rate constant. Okay, so that's the collision efficiency. Pretty straightforward. We don't really have a good way of describing or of finding that in practice aside from doing an observation, right? So this is something that we could solve for given a particular condition if we knew all the other parameters. I think there's maybe going to be a homework problem like that, or I've used one before, where you solve the mass balance, you solve for the K so that you can solve for this piece, right? That's certainly possible, but it's not like we can say, okay, X ionic strength yields us this. It might be something we can arrive at as an observation. Okay, so that one's pretty simple, collision efficiency. And then this omega term is what we call the flock volume. This is an interesting parameter because we call it volume, but it's actually unitless. Because what we're really saying is it's the volume concentration, or the volume occupied by the particles given some volume of water. So this is not actually flock volume. This is what I'll say is flock volume per volume of water. So, which is why it becomes unitless, assuming we have the same units in both parts. So we want to make sure that we do get it to be unitless. So we'll say cubic meters per cubic meters is what we ought to aim at. And when we consider the volume of some particle, really it's the volume of one particle times the number of particles that are in there. Let's say we take 1 liter, right? We say maybe there's 10,000 particles in my liter. We would take 10,000 times the volume of one particle in that liter to figure out what volume of this liter is occupied by the particles themselves. Okay, so that's our flock volume in 1 liter. And then I suggest we scale that to cubic meters to get all the units across in the same manner, then we can solve. So we'll see our equation here is simply the volume of a sphere, the volume of the one particle sphere, times the number of those particles. We're going to go ahead and just stick with the initial particles. That's going to be the most common and the most useful typically, because we're always starting with some sort of particle. Volume should be conserved, so we could do this after a flocculation, but we're solving the rate kind of beforehand to figure out something about the flocculation, so this is why we're going to use n naught. Okay, so and dp here would be the diameter of the initial particle. So this is literally the volume of a particle times the number of the particles. And the number will be, so this is a number concentration, right? So this will be, we could rewrite this as number per volume. So the only issue here is, again, if we had particles per liter, we need to change that to particles per cubic meter. And if we had the particle diameter in millimeters, we need to change that to meters and cube the conversion properly, and then have our system. So flock volume is pretty easy to get wrong given the unit conversions, but it's pretty simple and straightforward in terms of what it actually means. Okay? Does that make sense? Okay, so with that, we've got the G, we've got this flock volume, and we've got this collision efficiency. That should give us everything we need to do in order to solve for K and therefore solve a problem. So get some paper out and work on this problem. We will, I'm going to give you like this as a little bit of a quiz. I'll write up the things, and I can, maybe be willing to answer some questions. I'll give you probably through the end of class if you want it, need it, and we'll have a little. I'll take your answers towards the end of class. So this will be a participation assignment. So this kind of follows up from our last example we looked at, 6.1. So 6.2 here says we have silt flocculation before sedimentation. So, I told you at the start that I think I had the one digit wrong, so the silt particles in the last example should not have actually sedimented. So given that, we want to improve them. And so the problem says to improve the settling, these silt particles in that previous example are completely destabilized. You'll notice that, right? We talked about kind of what that means. So completely destabilized by adding alum. And it's passed through, this water is passed through one of two side-by-side well-mixed flocculation chambers. So I'd encourage you to draw that up. The chambers are cubic, each with dimension being 3.5 meters. They are mixed with paddle mixers that input 2.5 kilowatts of power into the water in each chamber. I'll write up the equations we just covered in a moment, so you'll have those. The water entering the flocculation chamber contains 10 to the 5th particles per milliliter. And so the question is, what is the average diameter of the aggregates leaving the flocculation chamber? Chambers. Okay. So we're trying to get the average diameter of aggregated particles. This is fairly involved. So mostly I'm I'm getting a participation score here. There will be a small portion of that being whether or not you got this right. Okay, so don't sweat it too much, but give it your attention and effort. All right, so we said that K was alpha times pi times the omega G. I think this was divided by 4, right? I'm gonna skip back to double check that I have this right for you. The 4 on top of pi. All right, I think you have everything you need there. Let me know if you see something that you feel like you're missing, or if you have some question. All right, how close have you guys gotten? You got an answer yet? Not quite. All right, so I think that instead of giving you the actual quiz right now, what we'll do is we'll pick up here next time. I'll walk through part of it, give you 5 or so more minutes, and then I'll have you I'll get your answers then. So we'll pick this up next time. How do you feel about it so far? You feel lost or so kind of lost or not so good about it?
I think that going into it, I just need to get what exactly it is.
Okay, good. So that'll be a good place to pick up. That sounds good. All right, we'll see you guys on Thursday then. Thank you.